introduction, and thank you all for coming. Yes, so today I would like to explain this project that I've been doing during this time as my postdoc here, which was done together with Luca Leonforte and Margherita Valenza, Francesco, and Angelo. And since the title is a bit long, it's remote entanglement generation in cathode cavity arrays using local squeezing. I wanted to put this image to give a bit the message, which is what we can do in these kind of systems when we have squeezing in here. So I think maybe this is the part that will be a bit new for you that we have not heard before. Yes. So I would like to start with an introduction. So the kind of systems that we are considering are cathode cavity arrays. So an array of cavities, photonic cavities, that are coupled and therefore light can travel around them. So they are a waveguide. And here usually we have cavities and also, and potentially also quantum emitters, atoms coupled to this waveguide. And these systems are interesting because I think mainly, at least for me, the main motivation is that you can tailor and enhance the interaction happening in the system. Because you can control the waveguide, the couplings, and then you can control how this interacts with the atoms, and also mainly atom-atom interactions. And that's why here in these kind of systems, you can also study topological phases, sometimes non-Hermitian physics, we've seen some talks in the seminars here. And they can also be interesting for doing quantum technologies, because you can engineer here the couplings, you can do quantum simulation, and then with the atoms, the qubits, you can do some gates for quantum computation, and so on. And for any time you want to do something for quantum technologies, one of the main resources that you need is entanglement. And here this entanglement can mean photon entanglement, or entanglement between the qubit and the waveguides, or between the qubits. And in these kind of systems, we can see many effects. And I would like to show you two of them. One is what we call defects physics, which is what happens when we have one of these arrays of cavities, and one of the cavities is a bit different from the other. For instance, the frequency of that cavity is a bit different. It's slightly different from the rest. In this case, we know that then there is a bound mode appearing, so a localized mode of the electromagnetic field in the cavities that is localized around this cavity that is the defect one. And defect here doesn't mean bad. It's just one that is a bit different. And this can also happen when it's not slightly between cavity, but for instance, if you have an atom coupled to one of these cavities, then you can also see one of these localized modes appearing. In this case, it's an atom photon state. This was one effect that I wanted to mention. Then there's another one, which is considering even just one single cavity and thinking what happens if we apply squeezed light to this cavity. So, some driving, and in particular, the kind of driving that we are considering are two photon parametric drives. So this is a laser field that is implementing a Hamiltonian like this one, which is now not like a linear drive that would be proportional to creation of one photon, but proportional to creation squared. And this is happening at twice the frequency of the pump that you're putting in this laser. And this kind of Hamiltonian is coming from these two photon parametric drives. And here is sometimes it's also called squeezing, because what is happening to the modes inside the cavity is that one of their quadratures gets squeezed. So expanded, this is the Wigner function, for instance, of the cavity mode, would get squeezed or expanded along one direction and squeezed in the other. And this is the squeezing of the lemon, let's say. And because you are squeezing, so you can see that the amplitude of this field is increasing in a certain direction. Here you can modify what is happening in the system, and you can enter, for instance, the ultra-strong coupling between the qubit coupled to this cavity and the cavity. And then once you're in this regime, you can obtain highly entangled states between the qubit and the cavity. So then here we had these two effects, and what we did was think what happens if we combine them. So what happens is now we are thinking that we have an array, and one of these cavities is like a defect, but in this case the defect is applying squeezing. And that's why we call it local squeezing, because it's not squeezing in all the cavities, it's just in one. Let's say, for instance, the one that is highlighted there. And for this, I will show you in this talk how we can use this for being able to generate remote entanglement in the system. So there will be like two steps maybe. The first is using this local squeezing to be able to enhance the interaction between an atom and this array, and then be able to prepare an entangled state between the qubit, and we will see also one localized mode around in this cavity. And then later how to also use squeezing, but now with a time-dependent amplitude, to be able to transfer it to a cavity that is far away from the system. So this is the main idea of what I would like to tell you in this talk. Okay? And for doing this, I've structured it in like 3 parts. The first one is I would like to explain what is this localized bound mode that appears due to the squeezing, and then also how we can prepare this initial entangled qubit cavity state, and then how we can propose a protocol to be able to generate this remote entanglement. And then I will summarize and give you some output. So let's go to this bound mode that appears due to squeezing. So now I would like to introduce with a bit more detail the system and the kind of models that we are using. So we consider one chain. Now these balls will represent the cavities, the photonic cavities. And in one of these, let's say that one, we apply 2-photon squeezing, or 2-photon parametric drive, or I will constantly call it squeezing, or local squeezing. And then we consider a very simple model for the array. It's a type binding model, constant couplings between all the cavities, and real. So like the simplest thing that you can, the simplest array that you can consider, but with this feature of the local squeezing. And then the Hamiltonian is the one of the type binding model. Let's consider equal frequencies of all these cavities and a real hopping rate between them, nearest neighbor, and then squeezing, which is already in the frame that is rotating at the frequency of this pump. So we will have a term in the Hamiltonian that is proportional to eta squared plus A, which now, this is only the one, so the deviation or relation of a photon at the cavity N1. Okay. And then, what we can do is the first step that we do usually, which is to diagonalize the system. So now we can find a basis in which the Hamiltonian is diagonal, and with this we see that we have 2 kinds of normal modes. Yes.
Since we are in the frame rotating on the frequency of the drive, so now omega c is actually the detuning.
Yes.
Okay.
Yes. So omega c, the tuning, everything will be always a detuning with respect to the frequency of the pump. And now when we do this diagonalization, and I put a little star because in the next slide I will mention some details about this, but we can find the normal modes of the system, so the ones that diagonalize the system, and we find that some of them are, in particular one of them is a localized mode, and the other ones will be some band modes that will be completely different. So this would be the one, the green one there is the localized mode that we find. And in particular, this localized mode has a frequency that is isolated from the rest of the band, and it lies below the band. And we have found an analytical expression for the frequency of this mode, and we see that it just depends on the parameters of the system, and also on the squeezing strength of this drive. The stronger you squeeze, the more important, the farthest away it goes from the band, the more isolated it is. And the shape of this mode is an exponentially localized function, also with a certain localization that also depends on the parameters of the system. And here, I think the details for the presentation are not important, but we also have an analytical expression for this. And essentially you find this, for instance, this is the localized mode. It's mainly localized at the driven cavity. It also shares some amplitude in the neighboring cavities in the SDK. and it has a much stronger amplitude than all the other band modes. It would be like plane waves in this.
So Silvia,
Yes.
so like here you're working like, with how many excitation you're working? So like,
This is unbounded.
so you are not fixing the number of excitation. So and how many photons do you find in this localized mode?
It depends a lot on the amplitude. If the amplitude of the squeezing is high, you can get many photons, like, I don't know, 50, average number of 50.
But is there an analytical dependence?
Yes, yeah, you can find.
Oh,
And in particular, if the squeezing is small, then this localized mode is much less localized. It's something more shared, and you can also see that then the frequency gets closer to the band. And in the limit of very small squeezing, it would get back to being in the band. And then, this is, here you don't see, but this slide was a bit gray in the sense that this is a bit technical.
yes, just localized mode below the bound. So in other words, why use these local squeezing and use like photons tends to like it's somehow more energetically favorable that the photons tends to stick together.
Yes, I mean, I think how I understand it is that the squeezing is putting photons in that cavity.
Okay.
So you're constantly putting on photons. So then for me, it's kind of intuitively
So that they stay bound.
that they stay
instead
bound
of
there.
propagating.
Yes,
Okay.
yes. So now this is just a bit more technical slide, this one, which is on how we do this diagonalization. This is just in case you're interested. If you're not interested, you can skip 1 minute, and then it will be more physics. But this, I think the formalism is kind of nice. So I just wanted to say a couple of things. So the one kind of interesting thing about this is that, so if we want to write our Hamiltonian as a matrix, we cannot do it. So we need to use the number formalism, which means that we have to collect all of our photon operators, creation and annihilation. So you see here, you have both all the creation and then all the annihilation. And then if you do this, you can write it in this nice form, your Hamiltonian. The reason for this is that you want to be able to include terms like A dagger, A dagger. If you will not do like this, it will not be possible to have the squeezing terms. So this comes from the squeeze. And then you just, the normal modes that I was telling you are just a collection, again, also of B and B dagger, that diagonalize the system. And then the way that you can calculate these normal modes is not by directly diagonalizing the Hamiltonian, but you need to do one small step on top, which is first you need to build the dynamical matrix, which is the one that gives you the evolution of A and A dagger. And when you do this, you can diagonalize the dynamical matrix and then get your operators. And this is done with a Borel transformation. Okay? And this, just so that you get a flavor of what this is like in the single cavity case, when you're diagonalizing the system, you will find that the normal modes, which are B and dagger, it's not, so B is not only a combination, like a linear combination of all the A's, you also need the A dagger. And this thing will make some technical files, so there now you will not be able to separate so much A and A dagger. So you will need to do it. So I mean, in our case, this is just a generalization when you have many capitals. Okay, but this was a technical thing. You can forget about it. You're not interested. And then we have this bound mode that we have found here. Another question is, okay, what happens when we put an atom in the system? And it turns out that you find an entangled state between the qubit and the atom, and the qubit and the cavity. And this is like this when you are applying a very large squeeze in the cavity. And the kind of interaction that we are considering is just one atom coupled to only one cavity, so it's really coupled to one. And then the Hamiltonian is the Hamiltonian of the array, the frequency of the qubit, and then some normal coupling that exchanges interactions between the cavity and the qubit. But now here you see why I did this small detour. When you now express all these in the basis that diagonalizes the array Hamiltonian, you will find what we had before. So we have the frequencies of the system, which are all there is one localized mode and all the other modes, the frequency of the qubit, and then you have a coupling between the atom, so which, if you express A as a function of all the others, you will find some coupling between the qubit and the localized mode, and some coupling which is in the first part, and then some coupling between the qubit and all the other band modes. And in this case, you have both terms that conserved and the number representation, and some that do not. And this is because A now is a combination of B and beta. So then here the kind of interaction that you find is interaction between the qubit and these terms that are like James Cummings terms, but also some terms that are counter. And if you look at what are the kind of couplings that you find, you see these are the couplings, so the dots, right? The couplings to the localized mode, and then all the others is to all the other modes in the band. So it's mainly coupling to the localized mode. But the G term, which is this one, is very close to J. G. The J is very close to G. So then this means that you cannot neglect, you cannot do rotating wave approximation here. Because you need to keep also all these terms, because these are. What you can do is seeing these kind of things is that you essentially can trace out the band or even neglect it, and then this will be just a unit. Yes.
So you're starting from, let's say, an interaction which is already in rotating wave, right? Before you make this transformation, and then of course you end up with this, with the counter-rotating term because of the Wolff transformation.
Yeah.
But what happens to the relative strength of this rotating and counter-rotating if you start from an interaction which is not in rotating wave length? Because it seems a bit strange. First you do the rotating wave and then you say no, no.
The main idea is that usually in the first part you can do it because this is the bare coupling between the qubit and the cavity. The squeezing is boosting this coupling,
Okay.
and then makes it effectively large, and then you cannot neglect it.
Okay.
But it's not that the original one was beyond rotating. It's due to the squeezing. And then from now on, we will forget about the rest of the band and maybe talk about the interaction between the qubit and the localized mode. And in this case, if the squeezing is very strong, you can rewrite your Hamiltonian as something like your localized mode, the qubit, and then a coupling term that is something like this that you can think. It's like P times sigma plus of the qubit. So if you look at this is what is called the quantum traveling Hamiltonian. Okay. Sometimes this is with X instead of P, but it's more or less the same. So then, and this is true when in the limit of these two couplings, the counter-rotating and the non-counter-rotating, being very close to each other. And this happens when the squeezing is very strong. And then when you are like here, you can calculate the ground state of the system. And this is a very large, so highly entangled state. And in particular, it looks like, so it's a conditional state of this localized mode being a displaced state with an amplitude alpha, conditioned to the qubit being one eigenstate of sigma y, and the mode displaced with minus alpha, conditioned to the other state. That's why. So this we would usually call it like a cat state. Or once you trace out the qubit, it looks like a cat state for the localized mode. Yeah, so it would be like this state if the qubit is in plus this state if it's in minus. And this is something that is known in the sense that this is now an interaction between the qubit and one mode. So and these kind of models have been said before. But for the new thing for us is that for us this mode is a localized mode that lives in this array. And with this we have the ingredients that we wanted to generate this remote entanglement. Because what we will do is starts from this maximally entangled state. So then the idea is you turn on the squeezing, you do it pretty strong, so you prepare the ground state, or you like the case, or you prepare the ground state of the system, which is this kind of cut state or entangled cut state. And then we will want to now transfer this to being entangled to a localized mode that lives in a very remote cavity. We'll do this by now tuning as a function of time the squeezing both in the original cavity and in the cavity that we want to transfer it. Okay. So then now we are considering two parametric drives, one in the original cavity, one in the target cavity. Same phenomenon that I brought before, but now we have two squeeze cavities and it's a time-dependent amplitude of the squeezing. And then we consider, for instance, this time dependence. So the first squeezing is decreasing as a function of time, it's a cosine, while the other is a sine. So then initially you have only squeezing in the first, and finally you have only squeezing in the last. And then if you do this, what you see is that the frequencies of the localized modes will change as a function of time. So now this localized mode, this frequency that we have here, if there are two squeezings, there will be two of these ones. And how they evolve as a function of time is this plot here. So this is as a function of time, the frequencies of the system, and you see initially this was one localized mode, and then all the bands. And then as a function of time, because the squeezing is decreasing, it gets higher, and then there's a second localized mode appearing, which is this one, and then they do this kind of go back and then go back. And what is happening, maybe it's more clear to look at the normal modes, is that now we will talk about two normal modes or localized modes. There will be the lowest energy one and the second lowest energy one, so this is two. And essentially what is happening is that at the initial time there is only one localized mode, localized Casulleras cavity. At middle times, because there are two squeezings switched on.
Why in the first place are you considering time-dependent squeezing amplitude?
This is because we want to practically move the entanglement to a cavity that is far away. So then at the middle points, there will be two drives. So then there will be one local mode, so two localized modes that will be symmetric and an anti-symmetric combination of the two separate ones that we will have. And then at the final moment, the localized mode will be far away, so it will be localized at the second cavity. And then the idea is to now couple the qubit, the entangled state between the qubit and this mode, and then in this time-dependent way, adiabatically make it being entangled with that mode, which is now localized very far away. Yes.
Just a question. What is the time scale required to have it as a big time?
This depends a lot on I will talk about it a bit later. It depends a lot on the distance at which you want to transfer. The distance is close, then this time scale gets smaller. If the distance is far, it grows, and it depends on the overlap between these and so between the two local modes.
Okay, but like compared to the intensive time scales?
Yeah, later I have some plot. Yeah, that's actually a very important point. Okay, and then we can look at this at the time evolution now of the system. So we have the qubit coupled. Now we will consider mainly the interaction with these two localized modes. We will also neglect the rest of the band. So that then now we have some time-dependent uplinks, some forms. And remember, the qubit remains at the initial at this point. So at the final time, there will be no coupling because the mode is completely localized in the other in a position where the qubit is not. This is how the coupling is evolved as a function of time. And then there are the adiabatic part and the non-adiabatic part. As you said, so depending on the time scales, you can or cannot neglect the non-adiabatic part. And we try to make sure, so we also include in the simulations, and we try to make sure that we are fulfilling the adiabatic conditions so that you can just look at the derivative part, even though we include. And then we start with this initial entangled cut state. And the plots that I'm showing now are the state of B plus, which initially it is at. And then we make this protocol, so we switch this squeezing in the way that I showed, and we arrive at the final time with a different state, which is pretty similar at 3.5, but still a very highly entangled state. We can calculate, for instance, the logarithm relativity is still pretty high, and also the fidelities between the two states are pretty high. And this is when you want, for example, an example in which you are transferring to a cavity that is far away by 6 cavities. And you can also see what has happened to the logarithmic relativity between the cubic and these localized modes, and essentially it starts very well, or like very entangled at 1, then it decreases a bit, and this is the previous point is the middle of the protocol, in which the two B plus and B minus are very close to each other, and so on, maybe you can have jumps or. But overall, if you make it slowly enough and you detune all of the qubits so that it's not interacting with unwanted things, you can make this transfer work. And now the question is, okay, how does it depend on the distance? And specifically, you can see that this energy gap that will give you, it will give you a measure of how fast or how slow you can be, because you need to be slower than any possible transitions to the higher modes. This depends on the overlap between the two polarized modes, and for larger distance, you need longer times. And for instance, the maximum, you still can get pretty high. Here I did until like distance 8, more or less. This is the maximum entanglement that was logarithmic relativity. For this, and this is a comparison between the adiabatic protocol and also including the non-adiabatic terms. For these terms 9 and 10, I didn't simulate long enough. I should do it long, but it's not good. And the times that you need are something like this. So let's say, for instance, for this V16 that I was showing before, 1, 3, 4, 5, 6. I don't know, like you need 10 to the 2 times the hopping rate. So here you have a feeling of what are the time steps that you need for the chords to match. But mainly you up until like 8, or even maybe you can push until 10 or later. You can do this transfer still with pretty high entanglement, and here we also want to calculate exactly fidelities, which is a measure that is a bit more. Sometimes a bit strange. So this was the talk. So as a summary, I showed you how we can use squeezed light to generate entanglement in the system between the qubit and one localized mode. And also we use the squeezing when we do it in a time-dependent way to transfer it to a remote cavity. And the main ingredients are this photonic bound mode that appears with the squeezing, which allows you to enter the instant coupling regime and then you prepare these entangled states, and then the adiabatic evolution of this localized mode from one region to the other to be able to do this. And as an output, what we would like to do is, first of all, look if there are better ways to change the squeezing of function of time. So do some Option control, because this was sine and cosine. This is more like a proof of principle. It can work. How you can optimize this. And then also one thing that we would like to see is if we can, in the same way that we have generated qubit photon entanglement remotely, if we can also qubit. That's a way now to use qubit hardware and make the two qubits be entangled. So this was it, and very important. I would like to thank all the people involved in this work. I think you know them as well. And thank you also.
distance. Nice. Mentioned at the end about the optimality of the control, and I was thinking, could you also consider, so you are transferring entanglement from let's say allocation to another location, and you are just driving, you're just using the drive on these two locations. Could you also do something in the middle to that?
Yeah, it's probably better or faster to put it in the middle step because you're transferring from here and then here. Probably the conditions are better than to put it from there up. I think if you do it slow enough, I think it could work better here. That's something that one time for transfer is used. That's if you want to transfer really far away, sometimes it's better to do it in 2 steps. I mean, so I didn't think on how to optimize now, but yes. But the idea is to think on that level. So the main point is to see, okay, you probably want to optimize that the gap is as large as possible and far from the band, or maybe the first part of the protocol can be faster because it's not important that they are so close. And so there are many parameters, and this you can do with optimization.
Okay. Yes. Thank you.
Or just blindly say, okay, expand, write any function for your squeezing parameters and then optimize really kind of blindly.
Okay.
Thanks.
So also going back to the algorithms, can you complicate if you do some further to
That's something we have not done, but it would be better.
because then you also solve the problem of having the small gap.
Yes.
Your gap can get models as you want to do.
Yes, that's the way we would like to do it. Yes, because then you could make all these protocols faster, but ensuring that you're not jumping to the high level.
Any more questions? Not, I thank you.